Hello, I'm Dr. Dupre, and in this section we're going to discuss lines and planes in space. Well, let's begin with lines. We can describe lines very easily using vectors. So let's see how we do this. For lines in space, given a line in space, well, we first suppose that we know a point on that line and a vector parallel to the line. Notice, what information can it take to nail down a line? We all know that if you know 2 points on a line, then you've determined the line. But also, if you know 1 point on the line, that kind of nails it down except for the direction. And so as soon as you specify a vector parallel to the line, that completely nails it down. Well, in terms of that information, the point here I've denoted P with coordinates x1, y1, z1 is specific numbers, imagine. How does that nail down the point? Well, suppose we take an arbitrary point Q in space with coordinates x, y, z. What would it mean for that point to actually be on the line? Well, notice, if the point Q was on the line, then the vector from P to Q, that is with tail at P and tip at Q, has to be parallel to the vector V because the vector V is parallel to the line. So consequently, the vector PQ will be T times V for some scalar T. And conversely, if PQ equals T times V for some scalar V, that tells us that the vector from P to Q is parallel to V, and therefore, since V is parallel to the line, and the P is on the line, the Q has to be on the line as well. So there's no way around this. PQ equal TV is equivalent to saying Q is on the line. So in effect, this very simple vector equation expresses the fact that this arbitrary point QXYZ is on the line L. Well, how do we translate that into actual equations? Well, remember the vector from P to Q is the same as angle XYZ minus angle X1, Y1, Z1. And so that has to equal T times the vector V, whose components I've denoted as A, B, C, A, B, C. So that's T times angle A, B, C. So there's a very simple vector equation, and let's work with that a little and see how we can get the equations for a line. So here's our equation, x, y, z equals x1 plus y1, x1, y1, z1 plus t times a, b, c. In other words, I've taken the x1, y1, z1 vector and moved it to the right side. And now we use our component form of vector operations, and we see x1 plus ta is the first component, y1 plus tb is the second component, z1 plus tc is the third component. And so now we have a vector equation that just says two vectors are equal, and the only way two vectors can be equal is for all their components to be equal. And so consequently, I equate the corresponding components, and I get three equations, one for each component. You might notice here that this is a common thing that happens with vectors. Anytime you have an equation of two vectors in space that equates vectors in space, you in effect have three equations. What are they here? X equals x1 plus ta, y equals y1 plus tb, z equals z1 plus tc. Now, an alternate way to express these is, notice we can solve each one of these for t. For instance, t in this equation is x minus x1 over a. T in this one would be y minus y1 over b. And t in this one would be z minus z1 over c. So we could write the expression this way, x minus x1 over a equals y minus y1 over b equals z minus z1 over c. So these are two alternate ways of writing equations for a line. When we write it this way with the arbitrary parameter t, in other words, this parameter t now is allowed to take any real number value. As t varies from negative infinity to positive infinity, the x, y, and z that result will vary throughout the entire infinite line. In this case here, we've solved and we've eliminated the t. So where we have the t in, we call that the parametric equations for the line. And where we've eliminated here, we call that the symmetric equations for the line, which I've denoted as capital L. One thing nice about the parametric equations for the line is that to generate points on this line, I can simply take any values for t I like, and every time I plug in a value for t, pick any value of t, say t equals 0, gives me x1, y1, z1. If I pick t equals 1, that's x1 plus a for x, y1 plus b for y, z1 plus c for z. In other words, you choose t any way you like, put it in all three of the equations, it gives you a point on the line. Well, these numbers a, b, c, they are the components of the vector v, which is parallel to the line. And so consequently, they are in effect specifying the direction of the line. And so consequently, we are usually called these the direction numbers for the line L. So when you know the direction numbers for the line L, then you can easily write down the equation in parametric form. But one thing to keep in mind, any vector parallel to the line will do. For instance, if I replaced the vector v by 2v, what would that do? It would double all its components. That would double a, double b, and double c. So the direction numbers would now be twice as big, but it's still the same line. In other words, the direction numbers are not unique. They can all be multiplied by any common factor, and it still, in effect, specifies the same direction in space. Now, let's get back to the thing we typically do in geometry. We say 2 points determine a line. So if you're given 2 points, how are we going to get the equation of the line in that case? Well, notice, here's a picture of a line, 2 points, P1, P2. We just formed the vector with tail at P1 and tip at P2. So supposing that we know those coordinates of those points, for instance, suppose P2 has coordinates x2, y2, z2, P1 has coordinates x1, y1, z1. Well, we know that we can now use the vector for the vector v, the vector with tail at P1 and tip at P2, and so that has components x2 minus x1, comma y2 minus y1, comma z2 minus z1. In effect, x2 minus x1, y2 minus y1, z2 minus z1 are forming the triple of numbers a, b, c. That is the direction numbers for the line L. So you see, the information you need to specify a line is either 2 points on the line. If you have that, simply convert immediately to get a vector parallel to the line. Or anytime you know a vector parallel to the line, then you immediately go back to the parametric equations for the line that we have here. Now let's actually calculate some equations for lines from given information. For instance, in our first example, give equations for the line through -2, 1, 3 and 4, 6, 1 in both parametric and symmetric form. I've actually drawn a rough sketch here of these points in space. So I've drawn my rectangular coordinate system with, of course, x here coming out of the board, y to the right, and z pointing up. And so I've kind of sketched in perspective the little box that would have the corner point 4, 6, 1 opposite the origin, and the other box having corner point -2, 1, 3 opposite the origin. And so you can kind of see perspective drawing here that the line through those 2 points is kind of going to be starting from this point, which is behind the blackboard, and coming over here towards this point, which is considerably out in front of the blackboard. It's 4 units in front and 6 units over to the right, but only 1 unit above the xy plane. So we want the equation of that line. Okay, so what's the data? The 2 points are P2 with coordinates 4, 6, 1, and P1 with coordinates -2, 1, 3. And so we immediately say, okay, we want to get a vector parallel to the line, and of course the vector with tail at P1 and tip at P2 is certainly parallel to the line. In fact, it's just lying right in the line, isn't it? Okay, so we know then that we can immediately write this down in vector form as angle bracket 4, 6, 1 minus angle bracket -2, 1, 3. In other words, we would immediately subtract these components from the ones above and find V equals 4 minus -2, that's 6. 6 minus 1 is 5. 1 minus 3 is -2. And so there is a vector parallel to the line. Now remember to write down the equation of a line as soon as we know a point on the line and a vector parallel to the line, we can write it right down. We, in fact, have 2 points on the line, so at this point we can take our choice. You can use either one. For instance, I'll take P1 to be the given point on the line, and we get X, Y, Z, angle bracket, equals angle bracket -2, 1, 3, plus T times angle bracket 6, 5, -2. Now, in parametric form, this is a sort of a vector parametric form of the system of equations. So we could write that as x equals -2 plus 6t. Second components, y equals 1 plus 5t. And z components, z equals 3 minus 2t. How about in symmetric form? We just solve for t. In other words, move the constant term to the left and divide by the coefficient. So that would solve for t in each equation. So for instance, x plus 2 over 6 equals t, or y minus 1 over 5 equals t, or z minus 3 divided by -2 equals t, and so those have to all equal each other. Here are the symmetric equations, and of course, what are the direction numbers? 6, 5, and -2. 6, 5, -2. Those numbers are called the direction numbers because they're just the components of, in fact, this vector v, which specifies the direction of the line. In other words, this is the direction vector for the line. Okay, now let's look at another problem. Suppose we want to find parametric equations for a line that's parallel to a specified line, but through a point. Find parametric equations for the line through 3, 1, 3, and parallel to the line with equations x equal 4 minus 5t, y equals 7 plus 2t, z equal 2 plus 4t. Well, when we look at this, going backwards, we realize right away that this is equivalently in vector form, x, y, z equals 4, 7, 2 plus t times -5, 2, 4. In other words, here's our vector parallel to the line, and so if this vector is parallel to the line given here, and the line we want is parallel to this line, then this vector is also parallel to the line we want. It's parallel to our line, so we take v equal to -5, 2, 4, and we use the point given. So that would be x, y, z equals 3, 1, 3 plus t times -5, 2, 4. Or separating out the components in component form, rather in parametric form as a list of equations, x equals 3 plus -5t, so that's 3 minus 5t, y equals 1 plus 2t, z equals 3 plus 4t. Now you might notice that if I compare this system of parametric equations down here to the one up here, notice the terms with the t's are exactly the same. -5t, -5t, 2t, 2t, 4t, 4t. The only thing that changed are these constants, and so in our original equation we have 4, 7, 2. So in effect, this line we're given passed through the point 4, 7, 2, and all we have to do is change the 4, 7, 2 into 3, 1, 3, and that gets the answer. Now let's use vectors to see how we can get equations for planes in space. That is, for a given plane in space, we would like to be able to write down its equation. What information do we need? Well, let's think about it. Imagine the plane of my hand. That plane can have lots of ways to be tilted, and if you specify how it's to be tilted in space, it can be moved parallel to itself so that still just the tilt doesn't nail it down. To nail it down after we've got the tilt, we have to specify a point in the plane. That holds it still. Well, how can we specify the tilt? Notice in 3 dimensions, as soon as we have a plane, there's only one direction perpendicular to that plane, and so to specify the direction of the tilt of the plane, we can just take a vector perpendicular to the plane. That is, if we know the components of a vector perpendicular to the plane, then we know the tilt of the plane, and then if we know a point on the plane, that nails it down completely. So let's look how this works with vectors. Here, in this schematic drawing, I've indicated a plane in space. Now, the plane is infinite, and I can't really draw an infinite plane in space. I can indicate a line, but not an infinite plane. So what I imagine here is a sheet that's lying in the plane, so we're seeing part of the plane. It's at some angle in space. And here we think of this as picturing the vector which is normal to the plane, that is perpendicular to the plane. I've denoted this plane with a big capital P, a very fancy one, and over here is the point P1, which is supposedly a point we know in the plane. So notice then, if we know that normal vector, or any normal vector, notice we don't have to specify the length of the vector, just any vector perpendicular to the plane and a point on the plane, then that plane is nailed down. So from that information, how can we get the equation? Well, let's look at any point Q in space. I can draw the vector whose tail is at P1 and whose tip is at Q. And what we notice is that in order for that point Q to be in the plane, it's necessary that that vector lie in the plane, in effect be perpendicular to n, because n, of course, is perpendicular to any arrow in that plane. And so consequently, the vector with tail at P1 and tip at Q is perpendicular to n exactly when the point Q is on the plane. So the point Q has the coordinates x, y, z arbitrary, whereas the point P1, we assume it has coordinates x1, y1, z1. That's indicating specific numbers that we supposedly know. And so Q being on the plane, capital P, is the same as the vector P1Q being perpendicular to n. What does that mean here? P1Q perpendicular to n is the same as P1Q dot n equals 0. Remember, two vectors in space are perpendicular if and only if their dot product is 0. So here n is what we call the normal to the plane. P1Q then has coordinates angle x minus x1, y minus y1, z minus z1. And let's suppose that the n has components we know, angle a, b, c. So our equation is 0 equals n dot p1q arrow. That is, the dot product of this vector with this vector being 0 is the equation of the plane. So we just compute what's the dot product of this with this, multiply corresponding components and add it up. A times the quantity x minus x1 plus b times the quantity y minus y1 plus c times the quantity z minus z1 equals 0. Notice the form of this equation. In effect, it's linear. That is, there are no squares, no fancy exponents or exponentials or anything. Everything occurs in the equation is either constant or a linear expression of x, y, and z. The coefficient of x tells me that one component of the normal, the first component. The coefficient of y tells me the second component of a normal vector, and the coefficient of z tells me the last component for the normal vector. So whenever I look at the equation of a line in this form, I know right away that a comma b comma c in angles is the normal to the plane, or a normal to the plane, and I know x1 comma y1 comma z1 is a point on the plane. Now let's look at this equation a little bit in a little more detail. Here I've written it again. A times the quantity x minus x1 plus b times the quantity y minus y1 plus c times the quantity z minus z1 equals 0. Well, let's distribute through. That's ax minus ax1 plus by minus by1 plus cz minus cz1 equals 0. And let's move all these terms with the x1, y1, z1 over to the other side. We get ax plus by plus cz equals ax1 plus by1 plus cz1. Alternately, we could say this equation is saying a comma b comma c dot x comma y comma z angles equals a comma b comma c dot x1 comma y1 comma z1. But the point is, notice this is just a number. If I know components for a normal vector and I know a specific point on the plane, then that's just a number. We'll call it d. And so alternately then I can say the equation has the form ax plus by plus cz equals d. The coefficients here of the variables then are giving me a normal vector to the plane. And consequently, if I take any point that's on the plane, I will get d. That's what this equation is saying. Take any point on the plane, put it in here for x, y, and z, their components of the point. You'll get d, and if that point is not on the plane, you get something else. And so this is the simplest form of the equation of a plane, and when you see it, notice those coefficients are giving you the normal vector. Now, when it's in this form, you don't see a point on the plane. You can't tell one. And so in order to find a point on the plane, if you actually want to find one, then you actually have to solve that equation to find specific points. And notice there's many solutions because the plane is a two-dimensional infinity. For instance, to find a point, you just say pick a value for x and a value for y and solve for z. Or pick a value for y, a value for z, and solve for x, and so on. So it's easy to find various points on the plane that have easy solutions where most of the coordinates are 0. For instance, that tells you where the plane intersects the various coordinate axes. But in any case, when you see the equation in this form, that tells you right away what a normal vector is. And so, for instance, if I said, what's the equation of a plane parallel to this plane but through some other point? Well, you would immediately pick out these coefficients for the left side and then just put the new coordinates of the new point in right here on the right side, getting a new value for d. You then get a new equation. Well, we all know that 3 points determine a plane in space. Let's see how from the coordinates for 3 points that we can actually find the equation of that plane that contains the 3 points, of course. So find the equation of the plane containing points 2, 3, 1, 3, 5, -2, 2, -3, 2. So those are 3 points, and I'm going to call P the point with coordinates 2, 3, 1, Q will be 3, 5, negative 2, and R will be 2, negative 3, 2. So here I've drawn schematically 3 points in space, and at this point, you could plot these 3 points in a picture, but it's not going to be that helpful. A schematic is really all you need. Draw 3 points, and now what are we looking for? We know our plane contains those 3 points, and what we're looking for is a vector n, which is normal to the plane containing those 3 points. So first off, if I consider the vector from P to Q and the vector from P to R, those vectors lying in the plane, therefore their cross product is perpendicular to the plane, because notice the cross product of PQ with PR has to be perpendicular to the plane containing those vectors. Well, that's our plane. So consequently, to find a normal vector, all I have to do is form the cross product PQ cross PR, and that will be a perfectly acceptable normal vector. Now, at that point, we've got our normal vector, and of course we need a point in the plane. Well, we've got 3 of them, so it gives us lots of choices there. And so we can easily get the equation of the plane. So it's just a matter of computing with vectors, and so let's start computing. I've written the Q with 3, 5, negative 2, and underneath P with the components 2, 3, 1, R with coordinates 2, negative 3, 2, and P again 2, 3, 1. So our vector from P to Q has components. Angle 3 minus 2 is 1, 5 minus 3 is 2, negative 2 minus 1 is negative 3. On the other hand, PR has components 2 minus 2 is 0, negative 3 minus 3, that's negative 6, 2 minus 1 is 1. So there are the vectors PQ, tail at P, tip at Q, PR, tail at P, tip at R. And so what we want to do is, in effect, form the cross product of these two. So it doesn't matter in what order. I wrote PQ cross PR. We could do it in the reverse order, because all we want is a normal vector. And what does reversing the order do? It just turns the direction 180 degrees to the opposite direction. So here I'll just write the vector PR underneath. And so we need to compute the cross product. Remember, I, J, K, and we're forming the determinant in effect. So for our cross product, to get the first component, cover up the first column here and form the little 2 by 2 determinant. 2 times 1 minus, well, negative 3 times negative 6 is 18. So that's 2 minus 18 is negative 16, comma. Now for the second component, cover up this second column and form the determinant, and remember to change the sign. So 1 times 1, that's 1, and negative 3 times 0 is 0, so the determinant will just be 1, and changing the sign gives us negative 1. And now for the last component, cover up the last column. 1 times negative 6 is negative 6, 2 times 0, so we have negative 16, negative 1, negative 6 is normal. And of course, you might notice that's just the negative of the vector angle 16, 1, 6. That means, remember, we don't care about whether it points in one direction or the opposite, so we can just drop that negative sign and take as our normal vector angle 16, 1, 6. And so now we know that our equation is 16x plus y plus 6z equals some constant on the right side. How do we compute the constant? Just take any one of these points and put it in for x, y, z, and that gives us the constant. So let's do it. We have 16x plus y plus 6z equals constant. So let's use, for instance, 2, comma, negative 3, comma, 2 to find what the constant is. We replace x by 2, y by negative 3, z by 2, 16 times 2 plus negative 3 plus 6 times 2. That equals our constant. And so 32 minus 3 plus 12 equals, well, let's see, 12 and 32 is 44 minus 3 is 41. So that tells us our equation is 16x plus y plus 6z equals 41. And there we have it, the equation of our plane. Well, now let's see how we can use vectors to actually find the distance from an arbitrary point in space that's given to us from a specified plane. Okay, let's look at our picture again. Here's the plane in space, and here's a vector normal to the plane. And suppose we know a point P1 that's on the plane, and here is our point Q, X, Y, Z, which is somewhere in space. And what we'd like to do is find the distance from the point Q to the plane. Now remember, that means the distance from Q to the point in the plane which is closest to Q, and we find that by dropping a perpendicular from Q to the plane. When we drop that perpendicular, we will arrive at a point R that's on the plane, and notice what we have then. We have a vector from P1 to R which lies entirely in the plane, and then we have the vector from R to Q which is then perpendicular to the plane. Of course, you could find the point R in the plane, but to find the distance you only need to find the length of the vector from R to Q. So R is the closest point to this plane, big fancy P. And so we begin by looking at the vector RQ. Tail at R, tip at Q. Notice, because that vector is perpendicular to the plane, it's parallel to N. And consequently, what we realize is that RQ is in fact the component of P1Q, which is parallel to N. It's the projection of P1Q along N. And so that means vector RQ is the projection along N of the vector P1Q, which you can remember is given by the formula P1Q vector dot N, that scalar multiplied by vector N, and all divided by the square of the length of N. So there's our vector, which we could then compute, but we're interested in the distance, so that means we want the length of this vector. So let's calculate the length. So the distance is the length of the projection of P1Q along N. And so notice when we take the length of that, that's just going to be the absolute value of the dot product times length of N divided by length of N squared. And so we get a cancellation in the denominator of one of the factors of length N squared. So the end result is just absolute value of P1Q dot N divided by length N. Well, imagine then that Q is just some arbitrary point with coordinates x, y, z, and P1 being on the plane has coordinates x1, y1, z1, and our normal vector has components a, comma, b, comma, c. Well, when we put that into our formula, n is a, comma, b, comma, c, P1Q is x minus x1, comma, y minus y1, comma, z minus z1 is angle brackets there, it's a vector. And so the length of n is square root of a squared plus b squared plus c squared. We're taking the absolute value of all of that. Now we've done this before. We've taken the dot product of the normal vector with a vector of this form, difference of coordinates in each component, and notice what we get is the ax plus by plus cz minus the ax1 plus by1 plus cz1. That is minus all of that, which we moved to the other side of the equation and we called it a constant. We just noticed that's just a constant. In other words, the equation of the plane has the form ax plus by plus cz equals d, and what we've got here is ax plus by plus cz minus d, an absolute value divided by the square root of a squared plus b squared plus c squared. So for instance, notice that the point xyz is on the plane if and only if its distance from the plane is 0. That is, if and only if the ax plus by plus cz is actually equal to d. And so what our formula is telling us is if that we took the equation of the plane in the form ax plus by plus cz minus d equals 0 and put any point into that expression, take the absolute value and divide by the square root of the sums of the squares of the coefficients, then we get, in fact, the distance from the point xyz to the plane. So, for instance, if I'm looking at an equation like x minus 2y plus 3z equals 10, and I want to find the distance from this point, 3, 5, 2, to the plane with that equation, all I do is simply put these points into the left side, that is 3 minus 2 times 5 plus 3 times 2 minus the 10, all absolute value, and simply divide by the sum of the squares of the coefficients. And so there we would have it. Of course, we could calculate this 3 minus 10 plus 6 minus another 10. That would be 9 minus 20 is negative 11. We've got absolute value there, remember, so that's plus 11. And that's divided by what? 1 plus 4 plus 9, that's 14. So we have, 14. So 11 divided by the square root of 14, we quickly get as the distance from that point to the plane. Now, remember, the most important thing here is to keep in mind the geometry of what's going on. In particular, when I solved this problem, all I had to do was remember to take the projection from P1Q along the normal line. For instance, if I had two skewed lines in space and I wanted to find the distance between those two lines, well, notice all I need to do in effect is take planes which, being parallel to the plane determined by those two lines, even though they're skewed, and find the distance between those two planes. That is, if I take the direction vector for this line and take the direction vector for this line and form the cross product, I get a direction which gives me a normal for planes which will contain both the lines, and the distance between those two planes will then be the distance between the two lines. In other words, keep in mind the geometry of what's going on, and you'll be able to solve lots of problems using vectors.